So there is different alternatives to implement a microgrid control system, but the centralized one is the most popular or accepted. So the microgrid control system send these set points for the distributed energy resources and controllable, dispatchable, controllable loads, as well as defines whether or not the microgrid is connected to the main grid. Okay, so let me move to the next slide. Let's see how does it go. Okay, here is an example of microgrid. In this case, the energy service company exchange information with the microgrid through this microgrid control system. So as I mentioned, the microgrid control system is responsible for dispatching the distributed energy resources, or DRs, considering, for instance, power quality, economic and environmental criteria. In addition, it manages the transitions between the grid connected and island mode. In island mode, the microgrid central control system provides the DR set points to restore the microgrid voltage and frequency to close to their nominal values. This can be understood as a secondary control. Since the microgrid control system communicates with the DRs and the controllable loads via a low bandwidth communication channel, in the island mode, for instance, at least one distributed energy resource must be responsible to keep the voltage and frequency within the nominal values. So when more than one DR are responsible for controlling this voltage and frequency of the microgrid, so it's required to have this DR must have some power sharing mechanism. Okay, so traditional synchronous generators have this inherent power sharing mechanism. So, however, the inverter-based distributed energy resources should be properly controlled in order to incorporate this functionality. So this can be understood as a primary control. That's what we are going to address in this tutorial. Okay, let's move to the next one. So basically, there is two ways to control inverter-based distributed energy resources that are the grid forming and the grid following. Okay, so the vast majority of inverter found in PV and wind turbines that are in operation nowadays are controlled in the grid following mode. Okay, a typical block diagram of a grid following inverter controller is shown on the left. So the left you see this grid following inverter. So it has an inner current loop over here. No, let's see. Over here has an inner current loop and has a synchronization algorithm that play a key role here in taking the information from the grid and generating this angular position and frequency that is used to make it possible to inject into the grid the desired active and reactive power. The active power, for instance, can come from the DC bus, the outer loops that's called over here, the DC bus to keep the DC bus voltage constant, for instance, or can also incorporate some frequency support action. The reactive, on the other hand, the reactive power comes from the volt-var characteristic, for instance, or a step t equal to 0 to operate with the unit power factor. On the right, we see the grid forming inverter. So grid forming inverter usually have an inner control loop to synthesize voltage at the POC. Okay, so here in its classical form, we synthesize current, right? So here we synthesize voltage. There is a way to implement it to synthesize current as well, but no, its most popular way is to synthesize voltage at the POC. Okay, so the voltage reference then comes from this primary controller. That is the topic of our presentation today. Therefore, the inverter can be seen as a voltage source behind an impedance. Okay, so the primary controller is responsible for providing the active and reactive power sharing, which is the key characteristic to paralleling inverters. Okay, this is concept have been used in UPS, but also it is adopted for the microgrids as well. So yeah, basically, so what we are going to see today, we are going to see this block over here. Now we are going to focus on this primary controller block and see how we can implement it, what are the alternatives, what are the strong points or are the weak points of the alternatives that we have available in the literature. So Gris Forming Inverters, primary controller, let's go. So the goals over here of this tutorial is to recognize the difference between the three main types for primary controller. That is the Droop. Now the Droop, we consider two alternatives. The virtual synchronous generator, we also consider two alternatives, and dispatchable Vector oscillator. Yes, it's also considered two alternatives, but just one alternative is compared with the previous ones. Also, we want to use the conventional techniques like small signal analysis to define the parameters that these controllers have to be tuned in order to make these controllers to work properly. So okay. So also, this is what make it a little bit different what we have seen in the literature. So we have used this test-driven approach to make automated testing of this controller under different operating conditions. So this is even though the small signal analysis, for instance, give you a feeling of what's the relation between the states and the modes and so on, it does not address the case of a short circuit or large disturbances or saturation. And so the test-driven design make it possible to capture the waveform in different operating conditions and make the analysis and see what are the good and weak and strong prongs, as I mentioned, of these controllers. Actually, probably if there is time, we are going to show one way to implement the current controller and voltage limiter and the virtual impedance. So, but it's also attached in this document that we have prepared. Okay, let's move on. Primary controller for Gris Forming Inverters. Okay, let's see what we have here. The primary control has the following objective. Okay, the frequency synchronization, voltage control, power sharing when in the island mode, and power dispatch when grid connected. Okay, so this is the Droop control is the most popular primary controller. It has been reported for power sharing UPS since the late 80s. Here we consider two alternatives of implementation of the Droop control. So the synchronous generators are widely used in the conventional power system, and they have this inherently active and reactive power sharing characteristic. So the second controller, primary controller that we consider is the virtual synchronous generator. Okay, where the inverter and its controller emulates a synchronous generator. So the third alternative for implementing the primary control is the virtual oscillator. So it has its root in the linear type oscillator, And it has this feature of when you couple this oscillator, they have this power sharing characteristic that can be used to control inverters in a grid with multiple DRs. Okay. Basically, we're going to start with the inductive Droop. The Droop control has its principle on the operation of synchronous generators, where the active power is linked with the frequency and the reactive power with the voltage. Since they have inductive, synchronous generator has an inductive output impedance, and then they are connected to inductive network. So we decided to consider the Droop, inductive Droop. There is alternative to work with, I would say, resistive Droop, for instance, is another candidate for implementation of this primary controller, but we decided to address first the inductive Droop, since it has, I would say, link what is already implemented in the present power system. So the idea is that a local or remote secondary control will send the set points of active and reactive power, as well as frequency and voltage, to the primary controller. So in this case, it's implemented by the Droop control. The Droop will measure the active and reactive power at the point of connection of the DR, and then it is filtered and passed through this Droop coefficient. Okay, that's linked the active power with the frequency, and then links as well as the reactive power with the voltage. Okay, so it's important to note here that in low voltage network, for instance, the equivalent impedance seen by the inverter is not always predominantly inductive. But you can use an inductor, or you can use a virtual inductor embedded here in the controller to make the output characteristic of this DR, or this inverter, inductive. So if the circuit is not inductive over here, so you can make it through this virtual inductor, you can make it inductive. Okay, let's move on. So in order to understand the behavior of the Droop control and tune its parameters, it is possible to assume that the converter is operating in sinusoidal steady state, where the dynamics of the inner loops and current loops are neglected. So, for this analysis, we are going to not consider this dynamics of the voltage loop, the current loop that might limit the current here. So we see that there is a strong correlation between the voltage reference and the voltage at the POC. So, of course, you have to take into account these virtual inductors that here are represented by this reactance XL. So this is the equivalent circuit that can be used to describe the dynamics in sinusoidal, quasi-sinusoidal steady state for the Droop control. Okay, it is easy to demonstrate that the active power delivered by the DR and the reactive power exchange with the grid are given by these equations. So if we consider that the voltage at the POC is constant and the power angle is small, so we see that there is a strong correlation between the power angle and the active power delivered to the grid, and the voltage and the reactive power exchange with the grid. So yeah, this is somehow motivate this use of this Droop control. So in order to obtain the dynamic model that described the droop control, so we have to consider all the relevant dynamics that are in the loop. So the first one is this low pass filter. So this low pass filter, attenuates the frequencies components that we will have above the grid frequency, for instance. So we use a low pass filter over here. So this steady state equation of this low pass filter is shown in this slide over here. So now if we combine this equation from the filter with the droop coefficients, we can have this dynamic equation that describe the behavior of the frequency command of the inverter and the I call it this inverter background voltage because there is this the drop across the reactance. So the voltage at the inverter terminals is basically the one at the POC. However, the dynamic variable, the state variable that is used over here is I call the inverter background voltage. So this is the equation that governs these two quantities over here. However, it's still missing the equation for the power angle. Okay, so if we look to this this theta here is the angular position. Okay, it's the angular position of the voltage synthesized by the inverter, I would say. So it is related with the frequency. So the time derivative of theta is equal to the frequency. So also, if you consider that the grid frequency doesn't change significantly, so we can see that this angular position will be equal to this the frequency of the grid times the time, plus the power angle. So if you are interested in the dynamics of the power angle, so you take the time derivative, and then you are going to see that the time derivative of the power angle is equal to the common frequency of the inverter minus the grid frequency. So if you so we have now this equation that govern the Droop controller when connected to a stiff grid. So this equation can be simplified if you define some constants here. So you see this that the non-linearities associated with these frequencies is actually in the product of the state variable E and the sine of the power angle delta and the E and cosine of this power angle delta. So this is the dynamic equation that may reveal what are the modes of the system. So since it is nonlinear, so you can use linearization around one operating point in order to understand what's going on with this, how these parameters, how the coefficient M, how the set point will impact the stability, or how fast or how slow will be the modes of the system. So to compute the equilibrium points, we set the derivative is equal to 0, solve for the state variables. So the equilibrium points are given over here. So we see two equilibrium points. So actually we are interested in the stable equilibrium points. So in order to find out which equilibrium point is stable, so you can look to this eigenvalues of this Jacobian matrix computed in around one operating point. So let's make an example here. Let's suppose that we have the Droop coefficients as 5% for the frequency, 10% for the voltage. We set this low pass filter at 12 Hertz, selected the virtual inductance as 2 millihenries. It's a little bit large here. You see that 0.75 pu. No, ohms. I don't know how many PUs. 0.5 pu. Okay, 0.5 pu, around 0.5 pu. So if you compute these equilibrium points, we see two equilibrium points over here, one with power angle 27, another power angle quite large, 157 degrees. So basically the stable one is the one that has the first one, that is I am with the mouse. We see the second equilibrium point has a real eigenvalue with the positive value, now indicating that the system, the equilibrium point is unstable. So we are interested in this equilibrium point. We have, we can, once we have this equilibrium point, we can investigate, for instance, the steady state behavior, whether or not this, given a reference of voltage or given a voltage, it will have the droop characteristic that we desired. So if you look to the frequency active power characteristic, we see that it is as desired. So we set here a 5% droop characteristic, and then when the frequency is 0.95 pu, we are delivering the full capacity of this DR, so indicating that it behaves as desired. Okay, we see a coupling also on between this active and reactive power, but it's not that relevant. So what concerns more is the droop characteristic of voltage, active voltage var characteristic. So we have set it to 10%. So we expected that when the voltage dropped to 10%, it would deliver the 1 pu of reactive power. However, it's if we selected this XL to 0.13 pu, it delivered a little bit more than 40% of the rated capacitor, rated capacity of the DR. So in addition, if you change, if you pick up another virtual inductor, so you see that this amount of reactive power or the droop characteristic depend on the virtual inductance. Okay, so this is a kind of undesired feature here, or less you have to be aware. If you are aware, maybe you can use this in your favor. But I would better have, if I put here 10%, I want 10% there, 5% here, and so on. So let's return to this qualitative behavior to see how this eigenvalues are associated with the state of the system. So you could look for the eigenvectors, but it depends on the units and the scale. So we decide to use the participation factor. So here is a participation matrix, and then this participation matrix points out that the frequency command and the power angle, they are associated with this pair of complex eigenvalues. And then you have a real eigenvalue that is associated with the amplitude of the voltage. So here is an example that try to demonstrate that if you change the droop coefficients, you are going to change also the dynamic performance of this droop control. So you have 5% for the frequency, and then 5% for the voltage droop characteristic, and then we have this behavior. But if you change to 10% for the frequency and the voltage, so you end up have a faster response. So somehow the dynamic performance of the droop is associated with the droop coefficients. Of course, you still have these two other parameters to tune, so you can play with these ones too. That is the power, the filter, the low pass filter that filters the power, and the virtual reactance or virtual inductance in this case. So this is a similar result over here, so in a different time scale. that where the power changed from 1 pu to -1 pu to 1 pu. Okay, so we see here that when there is this sudden change on the reference for the reactive power, the response is very fast. This is good somehow. But you know, I expected 33 kilowatt, but kVr. Actually, we are getting almost 5. Right? So this is we had been already predicted by the steady state behavior. Okay, here instead of the transient coming from the reference of active and reactive power, the transient comes from the frequency dropping from 60 to 55, 57 hertz. So we see that it supports the grid. As the frequency decreases, automatically the power is increased from 0 to 1 pu, I would say. Similarly, when the voltage drops, and also there is an increase here in the reactive power. The implementation of this Droop control is straightforward, right? So you have to, from the currents and voltage at the POC, you have to compute the active and reactive power. So you can use instantaneous power theory to compute the active and reactive power. Since we are dealing here with a single phase converter, so we needed to, it's interesting to, to have the current and its quadrature component at 60 hertz, the voltage and its quadrature component at 60 hertz. So we have to use a filter. Here we have used a second order generalized integrator to implement these filters. So basically the Droop is 2 lines implemented Droop here, right? And then once we have the frequency, we have to integrate the frequency to obtain the voltage angular position. So basically what's happened is that you have the reference voltage that is the amplitude comes from the voltage var loop, and the frequency comes in theta, and frequency comes from the frequency watt loop. Okay, so of course this is you have to also include the virtual inductance drop, but this is part of the another routine, so I'm not going to show this one. So here what we have noticed that we had this error, steady state error. In order to compensate for that state, you can introduce an additional integrator on the voltage loop. So we have now 2 additional parameters, actually 1 additional parameters. Actually, these 2 parameters are related with the Droop coefficient n, that relate to the reactive power and the voltage. So this gives an additional degree of freedom, and it solves the problem of this steady state error that we had on the voltage var characteristic. Basically, the dynamic equations that govern the operation of this Droop control connected to the grid are given over here. So it's similar to the previous one. There is an additional state that's associated with the integrator that we have added. So if you now compute the stable equilibrium point, and then we see that we have the desired voltage var and frequency watt characteristic as we designed, 10% and 5%. Okay, so it does not depend. Also, you can change this virtual inductance or the reactance, and so it will not change this I would say this voltage var characteristic. The eigenvalues also, the participation matrix also reveals the relation between the states and the eigenvalues. We have a pair of complex eigenvalues associated with the power angle and the frequency, and then you have 2 real eigenvalues. One of them associated with the voltage and another one with its derivative. Actually, the derivative is the fast one and the voltage is the slower one. The time response for the step change in the reference power is similar to what we had before for the Droop with one integrator. Now the step response for the change in the reference of reactive power, it is follows the dynamics of associated with the coefficients that that we have decided KV and KP, and in the steady state it converges to the desired reference. So the response to a sudden change in the frequency, the grid frequency, also it's similar as the conventional Droop. So here for the step change on the voltage amplitude at the POC, we see that there is one step, I would say here, close, that is similar as a conventional Droop, and then it follows the pattern defined by this the mode associated with this voltage itself. The implementation is a little bit more complex, but not that much. It's just this line that you have to introduce. That is an integrator, right? That integrate the error and the reactive power error also. Okay, so I wouldn't say that it will be significantly different than the previous one. As a summary, we have this, the selection of Droop coefficient impacts both the steady state and the dynamic behavior of the inverter. So this is one feature of the Droop. For the derivation of a small signal analysis, so if you design properly the inner and voltage current loop, you can neglect them. And then you can analyze just the primary control. The use of an additional integrator improves the steady state characteristic as we expected. So the virtual inductor also, even though that we have one feeder, I would say that is pretty much resistive with very small impedance, the virtual inductors also is predominant, and so you can use the inductive Droop approach to make the power sharing. And the implementation is straightforward. Okay, so with this preliminary analysis, we finished this Droop, and then we move to a second type of primary controller, that is the virtual synchronous generator. Virtual synchronous machine is a broad term, and it covers several implementations that mimic the synchronous machine dynamics using a static converter and its controller. The primary motivation behind the adoption of these virtual synchronous generators is that in a multi-converter power grid that operate according to this concept, it would render the overall system stable, like in a conventional power system that is dominated by the synchronous generator. Yeah, this is so the idea is once we implemented this, we are going to have these desirable features of the synchronous generator. And then, of course, it's worth mentioning that the inverter-based distributed energy researches can exhibit inertia, for instance, that we have in synchronous generator, and damping also, similar as a synchronous generator units. However, it depends on the energy storage capability available on the DC bus. Okay, in practice, to mimic inertia is necessary to provide energy to or absorb energy from the grid in order to implement this. So we are not addressing this issue associated how we are going to store or where this energy will come from or go to when providing this support to the grid. So this depends on the application, whether you have a supercapacitor or whether you have wind turbine where you can store energy in inertia, or take energy from the inertia, or you have a battery over there where you can store energy in the battery or recover energy from the battery. So yeah, so this is means we are not addressing this, but anyway, if you this is very important as well. So let's look for in order to implement this virtual synchronous generator, right? We have to derive a dynamic model for the virtual synchronous machine. At the left, we see a two non-salient pole, three-phase uniformly gapped synchronous machine. The stator windings are identically sinusoidally distributed and displaced by 120 degrees. The rotor is equipped with field windings over here. For simplicity, the magnetic saturation of the rotor, the machine, magnetic saturation of the machine is not considered. Since the stator does not have a neutral, we have a three-wired, we have no neutral connected over here. It's common to represent the machine in orthogonal frame, or here we call alpha beta frame. So we make this Clark transformation, and then we have this machine in what we call here alpha beta transformation, or alpha beta frame. Sorry. So the voltage equations are, we have a resistive drop that usually, you can consider, or you can consider very small. And then you see that the voltage at the terminal of this machine depends on the time derivative of the linkage flux, where the linkage flux depending on the stator inductance and then the rotor inductance, mutual inductance, I would say, and then the currents. So you can express this voltage, the voltage at the terminal of the machine as this equation over here. So where E is the EMF of the machine, that depends on the flux. So we actually, in our implementation, since we are dealing with a synchronous, virtual synchronous machine, we are not considering the current over here. So we are considering that we are able to manipulate directly the magnitude of the flux. So what else? So if you take the time derivative of the energy stored in the field with respect to the rotor angular position, it's possible to obtain the electromagnetic torque. Okay, so the electromagnetic torque will depend on the flux and currents, as well as now on this product, depending on the angular position. So in summary, so the machine, we have these three equations over here. Okay, so basically in power system analysis, it's usual to consider positive current flowing out of this machine, because it is a generator, right? So we have to change the sign of these two quantities over here. And then we assume in this case that is this torque, electromagnetic torque, is positive for generation action. Okay, so this equation here comes from the second Newton's second law, actually, that is associated with the swing equation. Okay, so basically, so this is moment of inertia. Okay, and then you have a damping coefficient over here. This damping coefficient will be the one that will define the droop frequency but characteristic. The another quantity that we are interested is in the reactive power. So we consider two cases over here: the reactive power computed at the gap, or the reactive power computed at the point of interconnection. So the block diagram of the implemented virtual synchronous machine is shown over here. So let's see, what can I say about this? Yeah, you can see here this block over here implements the virtual inductor, okay, and resistor. So actually, we add an additional pole here since this transfer function is non-causal. So in order to make it causal, we introduce additional pole in this transfer function that will affect the behavior of this reactance in the high frequency end, where the droop control is no longer have an effect. So basically, we see this part over here that is associated with the swing equation. We have this additional feed-forward compensation for this dumping that changed the operating point. So we want to, when we want to have an operating point at the frequency omega 0. So we added this this additional component to this the summation of these torques. So the input torque is obtained from the reference of the active power. And then we have the measurement of the current at the POC, the voltage at the POC. You go through the second order generalized integrator, and then you obtain the current vector. We obtain the magnitude of the voltage vector, and then we compare. Here you should divide by square root of 2 actually, because it's these quantities are RMS quantities. Okay, so let's move on, and then what else? Yeah, from the set point of reactive power, and then we compare it with the either with the power that comes from the gap, computed in the gap, and in the second case with the power computed at the POC, and then integrate it, and then goes to the set equation that we have derived, and then you obtain the reference for the voltage to be synthesized by the inverter. So now we want to have a look as well in this dynamic behavior of this virtual synchronous generator. The equation that govern the system are given over here. We have states as the frequency command, the power angle, and the flux, the magnitude of the flux. Okay, so also it's nonlinear. This equation is. There are the non-linearities, right? This is the square of the state variable omega times the square of this flux, magnitude of the flux. And here has product, again, the two state variables times the cosine of power angle. So here again, we have another non-linearity. Okay, so we define some constants over here. So if you want to compute the equilibrium point, and then we follow the same procedure, and then compute the equilibrium point, the Jacobian matrix, the eigenvalues of the Jacobian matrix will give you the possible stable operating points of this virtual synchronous machine. So let's run an example. We follow the same example, single phase 33 kilowatt kV inverter connected to 220 60 hertz grid. The droop coefficient here have been set to 3% and 10% for the voltage. So the impact of this droop coefficient on the operating point can be visualized in these two graphs. You see that if we keep this EO here is the reference for the voltage, right? And then this is the Q0. So if the voltage at the PCC increases with respect to the reference voltage, so what's happened, it absorbs reactive power. If it decreases, it delivers the reactive power. The same for the frequency. If the frequency is nominal, he's gonna dispatch this active power P0. However, if the frequency increases, what's happened is that the power, active power delivered will reduce, right? If it decreases, it will increase. So basically, now this is somehow it's a little bit different from the conventional droop, since we have this degree of freedom to define the time constants associated with the voltage and the frequency loop. So this is first time constant is associated with moment of inertia, and the second constant of k is associated with the constant k here. So we can, once you define this time constant associated with the frequency and the voltage, you can get this coefficient now, and then proceed with the analysis. Since this is a qualitative behavior that depends on the operating point, it's interesting to have a look at what's happened if you change the operating point once you give in a setting of parameters. You see that the complex eigenvalues doesn't change that much. And then, however, the real eigenvalue, it changes depending on the operating point that you have. Here you have a P, Q plane, and then, so when the P 0 and Q minus 1, we have one case where the eigenvalue get closer to the imaginary axis. See, and then again, we see that the participation factor reveals that the pair of complex eigenvalues are associated with the frequency and the power angle, and the real eigenvalue associated with the flux. So we see that the transient response for a step change in the reference, it's quite oscillatory. So we look in the literature. There is nice papers published addressing the issue of how to dump these modes, and then we use a paper from that was published in Power and Energy 2018 by Dong and Sheng, and then we implemented it to dump very well. It works nicely, I would say. And then here showed the transient response for the change in the set point of reactive power. So yeah, we still want to have a different approach over here in the sense that we are computing the reactive power at the POC instead of computing the reactive power at the gap of the virtual synchronous machine. So we are going to find difference over here. So you see Q POC over here, Q computed at the point of connection. And then the second difference is that in order to compute the reactive, you have to have the voltage in a vector and ascended to make this vector product of the currents and voltage in order to get the reactive power. Again, I think this is also divided by square root of 2 because we are dealing with RMS quantities over here. So the dynamic equation that governs is similar as the previous ones, but we find that it has a little bit less nonlinearities. So it's, it's a little bit, you don't have that square product of frequency and flux. So we just have this frequency and flux product over here times sine. The Droop characteristic is, is as expected because we are measuring the reactive power at the POC. And then here, it's important to remember that the reference power is -1 pu. So that's the reason that is around -1 pu over here. So when we change the voltage, and then what's happened, it gives you the support of VARs as expected. When there is a change in the frequency, also it gives you a support in with active power as we designed it in this Droop coefficient, 5% and 10% in this case. I think it's opposite. Should be 10% for, yeah, it's 10, this is wrong here. It should be 10% for the voltage, 5% for the frequency. Okay. This transparency, the procedure to design the time constants are similar as we have defined. We have also, we continues to have this coupling, this two complex eigenvalues associated with the angular power angle and the frequency command, and the real eigenvalue associated with the flux. So this shows the step response. Okay, I'm going to move on. Okay, this is interesting to note here that we set a reference for -1 pu to 1 pu, and then we have this response according to the time constant that we have set. However, when there is a frequency change in the grid, it does not respond exactly as the time constant that we have set, but it also has another mode, okay, that appears here in the output. So I wouldn't say that it's another mode, so you have to represent it in a different way. Anyway, this is here. Somehow it's interesting to note this this difference. So here also, if the voltage drops, it is almost to instantaneously provide some reactive power up to 20% in this case, and then it provides the rest of reactive power and converge to steady state. Implementation is a little bit more complex than the previous one. So we start with this Droop that's very simple, additional integrator that's become a little bit more complex, not that much. The implementation now is a little bit more complex, but you know, nothing that you can, a couple of C codes can solve, right? In summary, two different virtual synchronous generators are implemented. By feedback in reactive power at the POC, we got better steady state response for reference tracking. Different from the Droop control, the virtual synchronous machine allow ones to set the frequency Droop characteristic in steady state and the moment of inertia similarly as a conventional synchronous generator. So this is no difference between Droop and virtual synchronous machine. The damping action that has been proposed in literature improved significantly, I would say. The transient response, damping that pair of complex poles. So, and also the small signal analysis, you can do this neglecting the inner loops associated with the voltage and control.